This presentation is on a basic chemistry review. Most of you would have had chemistry last year, and so this is just an overview of basic materials that we're going to need to know to get us into biology. So, in terms of basic chemistry, first thing we need to talk about is atomic structure. You're going to notice that we have protons, positive charges, on the inside of the nucleus. We have neutrons, which don't have any charge, also on the inside of the nucleus. But on the outside, we have the electrons. I'm sure everybody remembers that. Now, we're also going to see that besides the protons and neutrons being in the nucleus and the electrons being outside of the nucleus, the electrons are also found in certain levels or orbitals that can only hold so many electrons. And so when we look at those, we can notice that here, the first level only has 2. Well, with all atoms, the first energy level can only hold 2 electrons. The next energy level can actually hold 8. But if we're looking at carbon, we can only see 4 because that's all the number of electrons that it has. So it is not considered a full level out here, but this inner level is considered full. Now this brings us to what's called valence electrons. Now, valence electrons are the electrons that actually interact with other atoms, and that allows bonding to take place, ionic bonding, covalent bonding. And so we're going to get into that a little bit later. But one other thing that we need to talk about is how we can count up the number of protons and neutrons and electrons and give them a certain name. Well, if you want to know how many protons are in an element, well, you look at its atomic number, because the atomic number tells you how many protons are found inside of the nucleus of that atom of that element. Now, it also turns out that if you know the atomic number, which is the number of protons, you also know the number of electrons in a neutral atom. So we can see that this has 6 protons. It also has 6 electrons. Now, there's another number called atomic mass. Sometimes you could make a reasonable connection to what's called atomic weight. They're very similar, and for our purposes, we're just going to call them the same thing. But atomic mass and atomic weight, basically you're counting the number of protons and neutrons together, and that will give you the atomic mass. So you have 6 protons plus 6 neutrons, that's 12. So the atomic mass of carbon would be 12. Now, when we get into isotopes, we'll kind of put some more details to this. Now, moving on, we're going to talk about what's called electronegativity, and it's an affinity for electrons. It's like certain elements like to hold on to their electrons more than other elements. They are not only like to keep theirs, but they want to keep other elements' electrons as well. So we see the electronegativity chart here. This is low and this is high, and you can tell down here these are kind of low, and these are very high, and these are nothing. Now, if you remember, these are the noble gases, and they don't want electrons, and they don't want to give up any electrons. They're just content the way they are. Now, these ones down here, they're kind of on the light blue side, the whitish side, and they have a low electronegativity, which means basically they're going to easily give up their electrons. But if you get up here, these will not give up their electrons very easily, if at all, and they want other electrons. And so these have a great pull on electrons, and these do not. And so that brings us to electronegativity when it comes to polar and nonpolar bonds. So carbon and hydrogen are similar in their electronegativity. So when it comes to that, they're going to share, that's a covalent term, share their electrons equally. And I'll get into that in a little more when we talk about covalent bonds. But the idea of electronegativity is carbon is okay sharing equally with hydrogen, and hydrogen is okay sharing equally with carbon, and therefore they form something called nonpolar. That's an equal sharing of electrons right there. They're both sharing electrons, and that's covalent, and it's nonpolar, therefore it's an equal sharing of electrons. Now, if we move to oxygen and or hydrogen in this molecule of water, what we're going to notice is oxygen is very electronegative and hydrogen is not. And so what oxygen likes to do is likes to share the electrons with hydrogen, and hydrogen is willing to share its electrons with oxygen, but oxygen is more stingy and it shares it unequally. And therefore, oxygen, because it shares unequally and keeps the electrons most of the time, it becomes partially negative. Not full negative, but a partial negative. That's like a little delta right there. It's like a little D, delta negative. That's a partial charge. And over here, we have hydrogen with a partial positive. So hydrogen has the electrons less, oxygen has them more, therefore it becomes a little negative, therefore this becomes a little more positive, and that is what we call a polar bond. And if it's polar, like it has opposite poles on opposite sides, then we consider that a unequal sharing of electrons, and charges do start to appear from that, which is the reason why life is able to exist, because this molecule right here is super important, and it's called water, and water allows life to survive. But the reason it's able to do this is because it comes up with all these wonderful properties, which we'll talk about in just a little bit. Let's move on. So ionic and covalent bonds, I kind of quickly went over that a little bit, but if you remember from basic chemistry, ionic bonds are typically between metals and nonmetals. Metals and nonmetals. And covalent bonds are between nonmetals. Both of the elements are nonmetals. And what happens in an ionic bond is these elements, the metals, love to give up their electrons. So they just give them away. And the metals love to accept them, so they take them. The thing is, if you give up an electron, when this sodium gives up its electron, it gave away a negative charge. So it becomes a positive 1. Because it got rid of that electron over here. But this chlorine accepted the electron, so it became a negative 1 because it has now one more negative charge than it did originally. But look what happens. A positive 1 and a negative 1, because they're opposites, they attract to each other. When they attract to each other, they stick together, and that's what an ionic bond is. Covalent bonds, neither one of these atoms want to give up their electrons because they're both nonmetals, and so what they do is they share them. So that's the key thing in covalent bonds, is sharing. So quickly going back to our previous slide, we have a polar covalent bond, an unequal sharing because nonmetal, nonmetal, nonmetal. And this is going to be also a sharing because nonmetal with nonmetal, but it's an equal sharing because it's nonpolar and they're similar in their electronegative compounds. So those are both covalent bonds, but we're going to see some ionic situations in just a minute, because we're now going to talk about properties of water. Water is super important to living things because it's great at dissolving stuff. I'm going to put here an excellent solvent. Excellent solvent, not a universal solvent because it can't dissolve everything, but it's an excellent solvent. Properties of cohesion and adhesion help things stick to the water, sticking to water, and water sticking to other things. High surface tension, which allows little bugs and stuff to scoot across the top of the water. High heat capacity, or high specific heat, along with high heat of vaporization, really keeps temperatures moderate the temperature. And then there's changes in density. So we'll see that in a second. All right, so going back to the water and its polarity, because oxygen is right here with a slight negative charge and hydrogen is right here with a slight positive charge. Remember, I'm saying slight. But that means that one's negative there too. And what you find is there's this little attraction between the hydrogen and the oxygen of different water molecules. So there's actually the stickiness that takes place, and we call that stickiness hydrogen bonding. So it's between different water molecules. Now, here is water acting as a solvent. Now we can see that salt, sodium chloride, it's an ionic compound because the electron from one sodium, the metal, left and went to the chlorine of the atom chlorine because it's a nonmetal. And so they have this plus and minus charge. Well, because they have this plus and minus charge, it's easy for water to pick them apart. So you're going to notice, like right here, the partial negative oxygen kind of grabs onto that sodium. So does that one. And it kind of pulls them away. And this is part of the dissolving process where it's acting as a very good solvent. And you'll notice here, the positive of the water, which is the hydrogen, they start to attract to the negative chlorine, and it pulls them apart, and that goes away. And you can see that if you keep doing this, what's going to happen to this big lump of salt? It's going to get broken down, and instead of a big lump of salt, you got a whole bunch of little atoms of salt, sodium and chlorine, and therefore it has been dissolved. So that's how that works. Now, when talking about cohesion and adhesion, what we're really talking about is the ability for water to stick to water. That's cohesion. Water sticking to water, that's cohesion. So I'm going to draw a line right there. This is all cohesion right there. Water sticking to water. But if you notice this, water along the edge of the blood vessel here, that's going to be adhesion. Water sticking to the sides of a blood vessel. And that's all really important to keeping the blood flowing through our bodies. But also, if you think about plants, like water moving up a tree works by water sticking to water, but also water sticking to the side of the inside of the tree in the xylem so it doesn't fall back down. That's a better example. Here's that picture of a little insect foot right here, kind of sitting on top of the water, not falling in. And it's because of all of the cohesion of the water molecules making this almost like a sticky surface there, so it won't break. That's where surface tension comes from. Next, we have high heat capacity or high specific heat and vaporization. All we're talking about here in this is that water has to absorb a tremendous amount of heat or lose a tremendous amount of heat before it changes its temperature. So it can absorb a lot of energy or release a lot of energy before it changes its temperature. And that's really good for us, especially on our planet having 3/4 of it covered in oceans. That's great because the sun can beat on, down on it all day long, and it won't change it too much. And then at nighttime, we don't lose a lot of heat or as far as our temperature, because even if it does lose a bunch of energy, it has to lose a tremendous amount for it to change its temperature. So what happens is that the water moderates our temperature inside of us and on our planet because it has to absorb or release a lot of energy before it actually changes its temperature. The other thing is, when we're talking about vaporization, here, talking about evaporation. And it takes a lot of energy to break these hydrogen bonds and free a water molecule. And in this freeing of the water molecule, when it leaves, it's going out. That's evaporation. But it can only leave if it gets unstuck from all these down here. So when it does get unstuck from all these down here, it frees itself up and it can leave. And that's the evaporation process. And so that just happens over a period of time, but it has to absorb a certain amount of energy for that to take place. That's called vaporization. And it requires heat to do that as well. Now, When we're talking about temperature, interesting thing that happens with water is water expands when it freezes. Water expands when it freezes. And so it kind of spreads out from each other and forms this nice lattice crystalline structure that can trap air inside of it and keep it afloat. So liquid water is pretty tight. You can see how these molecules are kind of all jumbled up down here, but they're very spread out in the ice part up here. And so ice floats, and that's super important to all organisms that live under the ice because they will not get squashed and crushed by the ice, and so they have somewhere to live. So one of the important properties of water is that water expands when it freezes and forms a layer of almost like insulation at the top and doesn't fall down onto the other organisms down below. So next, we want to talk about acids, bases, and pH. One thing about water is that it's a neutral substance. And it's because if you look closely, sometimes you have a water molecule that falls apart. It's called the dissociation of water. And water will fall apart. So that's H2O into, it'll fall apart into a hydrogen ion and a hydroxide ion. And if you have an equal balance of these, then you have a neutral solution. If you have equal hydrogen concentration and hydroxide concentration, you have a neutral solution. So that's not an acid or a base, it's neutral. And we can measure this when we talk about like the pH scale. The pH scale is based on the concentration of hydrogen ions that are free inside the solution. And so if you have more hydrogen ions, that would be down at this end, then you're dealing with something more acidic. And if you have more hydroxide ions, then you're dealing with something that's more basic. But if you're right here in the middle, because you got equal, then that's neutral. Now, base. If we look what a base is, you can see that it's got a higher concentration right here. So this level is right here, and this level is way up here. So there's a higher concentration of hydroxide ions, therefore it's basic. And when we say that's basic, you're dealing with something that's up in this range, above 7 to 14. That would be basic. Talk about acidic. Now you have a higher hydrogen ion concentration compared to your hydroxide concentration. So since you have more hydrogen ions, now you're dealing with something that is between 0 and 7. We can talk a little bit more about where those names or the numbers came from at another time. But that's just a basic understanding of that. So 7 is neutral, below 7 is acidic, above 7 is basic. Acidic substances have more hydrogen ions, and basic substances have, if we were to talk about basic substances, then you're going to have more, a basic substance is going to have more hydroxide ions and less hydrogen ions. So try to get that straight in your head that 7 is neutral, equal of both. Below 7, more hydrogen. Above 7, more hydroxide. Okay. So that's been a basic review, quick review of each of the major topics that we're going to need to be familiar with in order to kind of get better understanding of biology. So if you have any questions, we can talk about that at a later time.